Great, good. Again, thanks so much. Okay, Alec, I'm going to turn it over to you so that we can talk a little bit more about the utility of some other satellite observations for improving seasonal forecasts.
Great, thank you very much. Let me just share my screen here. Yeah, can you see that okay?
Yeah.
Great. So yeah, a bit of background about me for those that don't know. I'm a scientist at NASA Goddard and the University of Maryland. Previously did my PhD at UCL CPOM, the group that Rick was talking about that produces some of those cryosat-2 thickness products. Yeah, so I'm funded mainly through the Operation Icebridge Project Science Office, so trying to produce sea ice products for the community. So they mainly produce the sea ice thickness, but we're also trying to extend the utility of Icebridge products. One of the things I've been most interested in is looking at sea ice roughness and atmospheric drag coefficient over sea ice. So a quick shout out to a paper that's appearing in JGR Earth's Surface next week, hopefully. It's been in press for a while now. And also another quick shout out to a relatively new project that we're starting up here at NASA Goddard, and that's trying to improve our understanding of snow on sea ice. So I think this is going to be really interesting and exciting. We're trying to basically improve our estimates of snow on sea ice so we can improve our altimeter sea ice thickness based estimates, cryosat-2, and also thinking about thickness estimates from the upcoming ISAT-2 mission. So this is a NASA-funded project with input from ESA too. So I think we should have some really exciting presentations at AGU about that we're frantically trying to finish the abstracts for. Today I'm going to be talking mainly about some of the work I've been doing on sea ice forecasting. So this is something I started about a year ago, actually. You know, as a sea ice researcher, it seems like sea ice forecasting and sea ice predictions are becoming a more and more important issue that I wanted to get more involved with. And I wanted to kind of come up with my own little sea ice forecasting system. And so I'm going to present to you today just a brief overview of that forecasting model I have. It's extremely simple, but I think that's pretty useful because it enables us to try and understand what's driving the forecast. It's a statistical forecast, but using observations to drive that model. So I'll just show you some of the results we have, and then also try and look to the forecasts that are being produced this year. So these are forecasts that have been and are continually being submitted to the Sea Ice Outlook. Then I'll finish just by talking about some plans for the future. There we go. Yeah, so this is mainly, and also for context, some of these slides were shown at the Sea Ice Prediction Workshop in Germany. So some of you may have seen these already, but I've tried to update them and add in a bit more information about the current melt season. But I think some people don't know, and so I want to give a bit of background. This is mainly based on a paper that came out in JGR Earth's Future earlier this year. We use this very simple linear regression framework where we essentially apply spring Pan-Arctic data and try and forecast September sea ice extent. So the three products we use were passive microwave ice concentration. So we're using the NASA team data. We also looked at using this product, the passive microwave melt onset. So the date of melt onset over sea ice, also produced here at NASA Goddard. And we also compared this to the forecast produced using simulated melt point coverage in the sea ice model SICE. So this was a paper that came out in 2014 by David Schroeder and others from CPOM, which got a lot of press because it was really the first kind of real step forward in terms of demonstrating useful and skillful seasonal forecasts of September sea ice. So that was kind of our benchmark, really. We thought if we can't beat that, then we should just stick with what SICE is doing. So just a quick method slide. So the point here is that we copied the method that this CPOM team were using to derive their statistical forecast using SICE. So this is exactly the same method because then it allows us to better compare purely what the different input data are doing to change our forecast scale. So the first thing we do is we just detrend everything. So we detrend the ice extent for all years prior to our given forecast year. And we detrend every grid cell of either our observation or our simulated melt pond coverage. And then what we do is we just correlate the grid cells that are detrended and the ice extent. And so what's shown in these maps here are the weightings. So essentially the correlations between each grid cell. I think this is it's in June. And the sea ice extent. I can't remember. I think this is for all years prior to 2015. What we do with those correlations is we use them to determine weightings. So because what we're trying to do here is pick out regions that have historically been important for forecasting or correlating with sea ice extent. So we apply those correlations or weightings to the springtime variable that have been detrended already. And so we then generate this kind of weighted average time series of our springtime variable of interest. So sea ice concentration, melt onset, and melt ponds. One quick thing to note here is we can see how different all these variables are. So, sea ice concentration looks to be, the regions that look to be most important are kind of the northern Beaufort Sea region, and also regions in the Kara Sea and maybe some of the, I think that's the Laptev Sea there. Whereas the melt pond model, for example, seems to really focus on the central eastern Arctic region. So it's kind of interesting that these are, as I'll show you later, are working well for very different reasons. So as I said, we produce a very simple linear regression model from these time series. And then for our given forecast year, we detrend the data for that year and then apply that to this linear regression model and we produce a forecast. So very simple. And again, if you want to know a bit more about the detail of the forecast, read the paper or shoot me an email. And as I said, the nice thing about this simple model is that we can see what's driving the model. It's not a complete black box like some other statistical methods. So this is an example of the drivers of the forecasts in 2012 at the top and 2013 at the bottom. Years where we saw a very low sea ice, but then a kind of slight recovery in 2013. So in 2012, the sea ice concentration forecast was really driven low by low sea ice in the southeastern Beaufort Sea and some of the Kara Barents Sea. Again, not all of that data is used in the forecast, but you can see the hatchings kind of indicate regions that are included more so than other regions. The melt pond model, we can see that it was really driven by this strong anomaly in the eastern central Arctic, which kind of appeared in 2007 too. And then what we saw is in 2013, we saw actually positive anomalies compared to the trend. So again, these are detrended anomalies. So it's saying that there was kind of more sea ice in that southeastern Beaufort Sea in 2013 than we expected, which caused our forecast to be higher than what we expected from the linear trend. And similarly for the melt pond model on the right here, we saw less melt pond coverage than expected from the trend, especially compared with the year before. Yeah, and so this is all based on June data. We see for the melt onset in the middle, there's kind of less regions that correlate. So the melt onset tends to be really trying to pick out small regions that are potentially important in highlighting the triggering of sea ice melt. And then we kind of run this for every year from 1985 onwards. And as you can see on the figure on the right here, the colors are the different forecasts and the black is the actual observed sea ice extent, where this number here is less. So the numbers, the colored numbers are the root mean squared errors of the forecast, and the top is the kind of error, if you think, of the linear trend persistence forecast. So what you want is your root mean squared error to be less than that number, because this basically helps us define our scale of our forecast. So the approach we've used to define scale, which was similar to what David and the CPOM team used, was essentially comparing these root mean squared error terms. So it really tells you something about the accuracy of your forecast over a given range. And this was quite important. We actually had to kind of slightly tailor and improve on how that skill value was classified before, because these skill values are extremely sensitive to years that you get right or years you get wrong. And if you detrend things using linear trend persistence or some kind of climatological detrending, so we wanted to make sure that we're producing genuine forecasts and that we're comparing the genuine accuracy of those forecasts. A lot of people don't do that properly. Another method that we've seen a lot in the literature for kind of assessing how good forecasts are is to do this like autocorrelation approach, or it's essentially like a lagged correlation. So you just correlate your forecast with the observed sea ice extent. This is a very easy way of doing it, and it's still very important. It tells you essentially, obviously how correlated your forecast is with the observed. What I think this does do is it sometimes misses off giving you much of an idea of how accurate those forecasts are. You can obviously have a very high correlation, but you can have a constant low bias of what your forecast is compared to observed. And I think, we all know that sea ice extent is becoming extremely erratic, and we can have these real sharp departures from the linear trend, which is shown on the bottom here. These are the values, the departures from what we expect from the linear trend. And, we want to see how close we can get to those, really. That's the aim here. But I think this is an important discussion to always be having, is what is the best metric and which one should be using for different approaches. And yeah, I'm just going to move over this one pretty quickly, but this is kind of the results from all these different forecasts. And so again, we've got the skill value on the left here. So 1 means, our forecasts are perfect. Above 0 means it's better than the linear trend. And so we see a lot of these points at different lead time on the x-axis. So that's indicating that our forecasts have skill. And what we also do is we look at the skill of the forecasts from 2008 onwards, because that's when the sea ice outlook started. And so we can kind of see that, say, if we pick the blue line here with the circles, that's the sea ice concentration based forecast. And we can see they're all positive from March onwards even. And they really get better over time. So we see the sharp increase in the skill of our forecasts from May to June. The black squares indicate the melt pond forecast skill. So we can see that just using that simple metric of sea ice concentration, which we've had available to us for a while now, we can produce more accurate forecasts than the melt pond model. I do want to stress that these differences are actually pretty small. If we have 1 or 2 years where we produce really accurate forecasts, then your skill can change and move up pretty drastically. So I think it's still important to not just pick one. We can still get a lot of information from using multiple forecasts that all have positive skill for their own different reasons. So we're definitely not trying to say that we should be using this forecast instead of this one. We've definitely been talking and working with, say, the melt pond team especially, and comparing what their forecast is showing and what ours is showing, to try and see if we can produce a more kind of coherent sense of what the forecast of sea ice might be. Yeah, we did actually try and put these different metrics together in some multivariate regressions, but we actually found, despite what I just said about trying to bring everything together, we didn't see much improvement in our skill. That might be something to do with the kind of the problems of using the simple linear regression model. So I definitely want to try and explore more sophisticated methods of multivariate modeling in the future. There's been this idea that you can kind of overfit data when you have such a short time series. And so, yeah, I wanted to jump into 2017 forecasts. I think that's what a lot of people are interested in now. It seems like a timely opportunity to talk about this. We've been submitting to the Sea Ice Outlook. And so we started generating these forecasts in April. So on the left here is our forecast. So the black line is the observed September sea ice. The blue line is the forecast. Again, the bottom panel is the departures from the linear trend. And so, yeah, our first forecast was coming in at around 4.68, so extremely similar to last year, which came in at 4.72 million kilometers squared. And then if you look at the map on the right here, this is showing you the detrended anomalies that are driving this forecast. And I'm just showing sea ice concentration at first because it's, as I showed, it's producing the most accurate forecasts of recent years, and it's kind of the easiest one to understand. And so this forecast is being driven by, we're seeing some regions of negative anomalies, but actually kind of more positive anomalies as well. So these positive anomalies in the Greenland Sea and also in the Labrador Sea. Again, that region, the Labrador Sea, isn't really being included in our forecast because we're using those weightings, which are very low in the Labrador Sea. The Labrador Sea obviously becomes ice-free in summer, so it shouldn't really matter to our forecast of September sea ice. But yeah, it was interesting to see this pattern this year, and the NSIDC talked about this in some of their Arctic sea ice reporting, that there was been a kind of interesting pattern of, I think, what they called a cross-Arctic wind regime. So there's been high pressures over the Canadian Arctic and low pressures over the Eastern Arctic, which is causing winds to blow up over the through the Bering Sea, causing extremely early retreat of sea ice in the Chukchi Sea, where we're seeing some of those blues at the top here. But it's also causing ice, a pretty strong kind of transpolar ice drift. And also that combined with cool airs coming in from Scandinavia seems to be causing the sea ice conditions around the North Atlantic to be maybe slightly higher than we expected them to be. So that's been pretty interesting. But then we can see how this develops over time. So if we now switch to May, we can see those anomalies have just kind of amplified essentially. We've got this really strong anomaly in the Chukchi Sea. Again, it seems like that Chukchi Sea region isn't actually used in our forecast, which is interesting. Historically, that's not been a region of importance for May forecasts. So it'd be interesting to see if this is kind of the first time that kind of triggers a high correlation in our model. We're definitely experiencing record and unprecedented sea ice conditions in that region. But then again, we're seeing these high concentration regions, again, high relative to what we expect from the trend in the North Atlantic. So the forecast there actually went up slightly to 4.81. You can see again, the May forecast struggles to pick out the extremes. So, you know, we don't see this as gospel at all. But June is when we see a big increase in skill, and when we start to actually, well, me personally, I start to consider the forecast to be a lot more reliable. So the June forecast came in a bit lower again. So it went down to 4.5 now. Again, not enough to set a record. But June was when we started to see the Beaufort Sea, the southeastern Beaufort Sea opening up. Again, this is a region that is historically important for September sea ice forecasting, highlighted by the hatches here. And you know, this region has been identified by others, like Mike Steele had a recent paper about the increasing synchrony of the Beaufort Sea and the importance of this, the timing of this opening. We can see the Chukchi Sea anomaly is still present. We've got some other anomalies, negative anomalies forming, and those positive anomalies in the North Atlantic have kind of subsided slightly in June. So unfortunately, I don't have the July forecast. We kind of still have a couple of days for the rest of the June data to come through, the July data to come through, sorry. But it'll be interesting to see if these anomalies have persisted or if they've strengthened or changed during this month. It seems like the sea ice extent is still tracking very low in general to the 2012 levels. But let me just check the next one. Yeah, and just to give you an idea of another forecast, so this was provided by David Schroeder and the CPOM team. So this is the June forecast of September sea ice using their simulated melt pond coverage. And again, they're seeing a kind of similar, actually maybe slightly higher forecast to us, maybe around 5 million kilometers squared, not 5 meters, that would be fairly crazy. And they're using May and June data combined, and they're seeing this is driven by less than expected ponding in the Eastern Arctic in their simulations. But then one of the issues that we've been thinking a lot about is this problem of forecasting sea ice extent. So I realize I've been talking a bit long, so I'll try and skip through this pretty quickly, but sea ice extent is probably not the best metric. Sea ice area maybe tells us more information about the pole hole. And we think this is what maybe caused us some problems in 2016. We had this very unconsolidated sea ice cover, and forecasting the extent was maybe why our model and also the sea ice outlook forecast in general a higher extent than what we actually observed. So what we've done now is we tried to actually produce a time series of sea ice area, and we're forecasting that too. So this is now the June forecast of September sea ice area. So if I just go back to show you the 2016 problem there, we can see the actual observed came in at 4.72 in our model, and also a lot of others came in a lot lower. But now if we forecast sea ice area, we see this huge improvement in the forecast, and a kind of freakishly good forecast in 2016 too. Again, because we're now capturing, you know, the more physical state of the sea ice pack. And then the forecast of sea ice area is still not suggesting a record low for 2017. It's maybe fourth or fifth highest. But yeah, it'll be interesting to track what the actual area and extent are come September. And just very, very briefly, one of the other areas that was identified by the sea ice outlook as important is this Alaskan sea ice extent, which Rick talked about very briefly. And our model can also be used to produce accurate regional forecasts. And so we submitted these to the sea ice outlook too. And again, our forecast is coming in maybe a bit higher than it was last year. And again, we can do this for extent or area too. We're definitely trying to think about what metrics might be more useful to stakeholders in the region. So people have talked a lot about ice freeze up and ice advance. And so we're trying to get some time series of that to forecast too. I'm not sure if we're going to be able to do that this year or not, but we're definitely trying. And yeah, we definitely want to try and engage more with the community and think about what we want to be predicting. And then also looking to go beyond September, so we can try and forecast October or whatever. But I'll skip over that and just leave you with a couple of thoughts for what I want to do next. So as I said, I'm actually mainly funded through Icebridge and other missions. So this is kind of a bit of a side gig for me, but I'm definitely trying to think up new funding opportunities and what might be interesting for the community. And definitely one of the things on my to-do list is to come up with a more interactive user interface where people can kind of look at these forecasts and maybe even generate their own, especially as it's using all this near real-time data. And maybe we can help encourage a kind of community-driven forecasting framework that we can iterate on and improve on over that simple linear regression model. And then, yeah, the other thing I didn't mention was Antarctic forecasting, which was also solicited by the Sea Ice Outlook this year, which we've also generated, but I've not shown that, but I can share those two, and they're in the Sea Ice Outlook report. So thank you very much.